Hello, everyone, and welcome to my session on Data Lakehouse and why it implies and how it actually is based on open technology fundamentally. I'm Thorsten Steinbach from IBM. I'm working on the IBM Cloud Platform as an architect. I'm leading the Cloud Data Lake services there. And today I'm going to show you, I'm going to take you through a ride of open technologies and libraries that are all somehow driving and enabling and in combination, actually enabling this idea of a data lakehouse. To put it a bit in historical context, right? So this is just a more recent evolution that we are talking about on the history of big data systems. So it started off long ago with data warehouses, just a relational database that is configured for analytics workload and larger data volumes to scale out. Hadoop came along, opened up on multiple fronts, and that evolved further into more cloud native data lakes. And the data lake houses actually are now trying to solve a problem to bring this all together somehow. Right? Data warehouses are still around, so there is a reason for that, because they have higher quality of services in terms of consistency, security for data, and scaling and giving latency SLAs. And Data Lakehouse is really the attempt to bring this all together. To put it a little bit into topology, these big data systems serve a purpose. They serve a purpose of onboarding big data to analytics. So big data coming from different sources could be stored already on your premises with databases, systems of record, SAP systems, or it could be data that is produced as we speak, sometimes just exhaust data from logs. And the big data systems take on this data into, for instance, and then it has a life cycle of basically preparation, enrichment, and optimizing the data and the layout so it's ready for analytics. You can then analyze it in the data lake itself, but traditionally you often see data warehouses still coming in combination here, where the data lake is limited just to the preparation of the data, and then you ETL it into a data warehouse because it gives you interactive query, response time SLAs, and transaction consistencies, and so on. The downside of that is it's complex multiple systems, and even that combination doesn't serve well other more sophisticated analytic workloads like machine learning, AI, and so on. So the data lakehouse, the declared goal is basically to somehow solve that and bring this all together on a data lake architecture. So let's start with a more closer definition of what a data lakehouse actually is for our purposes here. So as I just said, a data lakehouse is a data lake, but it has additional qualities of service that actually normally just data warehouses provide you. So like a data lake, it is on disaggregated storage, like object storage in the cloud. It uses open formats on that storage, file formats, but it adds a new notion of table formats. We talk about that today. And it also has a central table catalog to decouple logical from physical data model. And just like data lakes, cloud data lakes especially, it's very elastic and heterogeneous, which gives you flexibility to mix and mesh different engines whenever you need it, bring it up and down for ingesting, processing, querying, and so on. And it's increasingly delivered or typically delivered as a service. Now, what are those data warehouse style qualities of services? That's what we are going to look at in the following, and I'm going to walk you through these details. Data consistency, schema enforcement, performance and scale, the catalog topic, data protection, and automation of pipelines. I'm going to walk you through those and explain you how open technology and open source actually enables that these qualities of service can now be delivered or will be able to be delivered. And open source is nothing new for data lakes. I mean, these data lakes have been dominated by open source all along. I mean, Hadoop itself is Apache poster child, Apache here, Apache there. And it's all about open formats, open multitudes of engines that you can, and open hardware even, right? Deploy on any kind of standard hardware. This principle of open source is entirely continued when we talk about data lakehouse. That's a fundamental thing that needs to be understood. This is not something that we're giving up on. And that's why we're going to look at these open source trends now that are relevant here for the lakehouse trend. Let's start with data consistency. So object storage, when you use object storage, it doesn't allow you to do data updates in place. New data has to be added as separate new files. If you want to do updates, changes, deletes, you have to rewrite files entirely. If you want to write larger chunks of data in a multi-threaded way, this could interfere with parallel reads. They don't see, you can't guarantee consistent reads, right, if such things go on in parallel. Not to speak of housekeeping that is needed, like reorganization and grooming and compaction of the data as it evolves and ages over time. You can't really do that in place in a consistent fashion. The solution is that you're introducing a new set of metadata that you're storing with the data, so that this metadata tracks versioning of the data and allows us to get in sort of transactional asset consistency. This is what table formats are about. We're going to look at in a second. Before that, we look at the schema topic here. Schema enforcement specifically. In a cloud data lake, any library, tool, engine can be in combination writing new data to the data lake. That's a strength of it. That's part of the openness. But the problem is that you can't guarantee that one engine, actually one library, one user even, adheres to the schema. Right? It could add a new file that's completely incompatible with your schema. The solution here is that writes and reads are done through a common library that actually enforces the schema, that tracks the schema when you write it. And that's also what the table formats are about. Table formats are about, that we're going to look at in a second. Finally, table catalog. In data lakes, starting with Hadoop, I mean, this has been a standard that has evolved over time. It's the gold standard of table catalog there. It's the Hive Metastore. The problem with the Hive Metastore is that if you really talk about large data lakes with six or seven digit number of files or even partitions, it really becomes a significant bottleneck. It just hasn't been designed for that. The solution for that is twofold. There are two parts of the solution. One is, again, the table formats, because they allow you to decentralize and relieve the central Hive Metastore or table catalog in general from a lot of duty. You put more metadata, push it down to the data itself. The second element is you still need a catalog. The table formats doesn't solve all of that, because you need to a cross-table perspective. You want to do maybe even transactions cross-table, data versions consistent cross-table. So you need a cross-table aspect, and the table catalog is for that. And there are actually a new generation of catalogs that are evolving in the open, like, for instance, Nessie by the Dremio guys or LakeFS. Another thing that is not really tackled yet, I want to call it out, that is needed as the next frontier, is convergence with real-time metadata for Kafka Schema Registry or Apache Registry to bring this together with the data in the Hive Metastore. Now, I've talked about these table formats all along. What are they about? So there are three table formats here: Iceberg, Delta Lake, and Hudi that matter today. And they're driven by the Netflix guys, Databricks, and Uber, respectively. They're all open source projects over the recent years, and they're all abstractions between physical files and disk, like Parquet files, and how they form and structure a logical table. This data is stored now in these table formats across multiple files, the data itself, multiple Parquet files, and metadata also. They are dedicated metadata files. Data is read and written through dedicated libraries only. These libraries need to be embedded and adopted by different engines. The libraries also include compound housekeeping functions like compaction and vacuuming that do this for you. And with that, these metadata files actually also give you scalability of metadata, because they have more metadata stored along with the data. With that, they support transactions and versioning on a per table level. So on a per table level, you can now get a snapshot isolation, a consistent view of this table data when you run a query. Parallel writes will not basically interfere here. You can even decide, I want to do time queries. I'm going to go back in time in this table. And also in-place updates and deletes are possible logically, because the magic behind the scenes is done by the table formats and the libraries. There are different strategies here. There's a copy on write and merge and read. There are different strategies that we don't have the time to review in detail today. And they manage also the schema of the table explicitly in the table formats. Iceberg is one of the candidates here. I want to look more closely as an example. Iceberg tracks all of the files directly. Directory structure, the directories don't play a role anymore. Naming of the directories don't play a role anymore. Writers create new data files Parquet, ORC, Avro, or even a mix of that. That's one of the features of Iceberg in the same table, and metadata files in place. And only when they are done doing that, there's a commit. And this is an atomic swap of a high-level metadata file that basically makes this new snapshot of data visible to all. So with that snapshots, right, you can have snapshot 0, snapshot 1 here. You have now the possibility to do time travel queries and even do rollbacks, roll back to previous snapshots. It supports copy and write and merge and read. Especially merge and read had some recent additions here in Spark 3.2 for the leads are now supported. And another nice feature of Iceberg is partitioning is totally abstracted from the consumers. So you can even mix multiple partitioning concepts in the same table, right? You can say my older data is, like you see it here, partitioned by month, and the more recent data by day, because I want to have more point lookups per day on the more recent data. And this is more efficient then for those queries. And partitioning can also be changing with zero rewrite of the data, just some metadata files need to be updated. Okay, so that's what Iceberg is about. I want to now look some other aspects here of the data warehouse qualities, performance. In data lakes already, there has been an evolution of best practices and standards of file formats that are supported there and recommended. It actually accumulated in the two formats ORC and Parquet being most popular because they are columnar, allowing for higher compression of data, having a lot of statistics included in the files, like for instance, the min and max value for each column in a file. Even Bloom filters are now supported. It means for columns that have a lot of unique values, it's an efficient statistics to basically know what basically is in this file, what kind of values on this file. And this is exploited by many engines such as Spark to do file skipping when you read this, right? By looking into these statistics. This, however, means that these engines have to read all of those files, at least the footer segment of that still, right? It's just a small part, but from all of the files, you need to read those footers to get this information. And it also doesn't cover more complex, sophisticated, state-of-the-art indexing schemes that data warehouse support, such as clustered indexes, which means indexes that include data so that you can do index-only queries where you don't need to read actual data at all. Another thing that actually evolved is the so-called Hive-style partitioning, which is just a naming convention of how you lay out file names and directory structure on data lakes. And this is also adopted by many engines to do data skipping based on those namings that are delineating what is a partition, what does it contain. But this means you can only skip on these partition columns and not have predicates and other columns you can't do any data skipping. The solution for that is to introduce dedicated indexing frameworks on top of all of that, in open source. There are two examples that I want to call out from IBM, what we have developed open source. This is the thing called Xskipper, and Microsoft is heavily engaging on the Hyperspace project. But it basically means that index data is now collected and stored in a dedicated set of Parquet files, also in object storage. And with that, you can index any format. You're not limited to Parquet and ORC only. Other formats can also be indexed. Here's an example of adoption of Xskipper in my own cloud, IBM Cloud. This is a Spark-based, or Spark-based service here, data lake service called IBM SQL Query. You can see you can do a DDL to create an index on the table, on a file actually, and say it's a Bloom filter. And then if the query comes in that you see at the bottom here, with some filtering for some specific unique values, this is now a very efficient filter that can be applied here. And you can see here that we are skipping almost all of the files, just a small fraction it needs to be read, and also just a small fraction of the data. And that directly translates into performance, right? I/O avoidance translates to performance here because of this aggregated storage. Okay, so I/O avoidance is good. So what's next here? I mean, one thing is obviously that these indexing frameworks, of course, need to somewhat combine with the other goodness that we saw before, which are these table formats. Hyperspace is already good, progressing well here. It's already available for Delta Lake support, and Iceberg is presumably coming up very shortly. But there are other ways to do I/O avoidance, like for instance, caching data. You can cache the raw data itself, right? The file data on disk in your engine. Dremio does that, for instance, with their so-called Arrow cache, the Dremio engine, where basically The Parquet files on disk are cached as arrow structures in memory in the least recently used algorithm. And another strategy is you do cache of intermediate results, sort of partially pre-computed data. Also here, Tremio as an example supports that with the so-called reflections, data reflections, where you declare certain joins, typical joins that should be pre-computed and cached. Okay, so those are all performance-related things that matter here for the data lakehouse. Let's now pivot to the security aspects here, data protection. For data protection, we're looking at two concepts. One is access control, the other is encryption. With plain data lakes and object storage, right, you can get access control on a per bucket level, and for some object storage also more fine-grained on a per object level. But you can't get more fine-grained. That's just not what the storage can do. Like for instance, on a per column level, right, to get access control here. Now you could think, well, I'm doing this enforcement then now on my engine and not on the storage level, but that means you're really locked into this one engine, and any other engine that doesn't adhere to that could bypass your access control. So it's not really something for an open lakehouse. So lakehouses, especially when you think of an open data lakehouse, needs actually fine-grained access control enforced in the files itself. On the encryption side, right, of course you can have storage level encryption, right, on the object storage, but that means you really have a high trust in your storage provider, service provider, and there are no bad actors and the operators and so on. And if you want to escape that, you also actually need something that's more independent of the storage, and you also need encryption actually in the files. And the solution for that, combined solution for both of that, that actually is available and emerging is encryption in Parquet. It's part of the open Parquet standard called Apache Parquet Encryption, sometimes also called Parquet Modular Encryption. It's independent of the storage, it's transportable, the data is trusted, but the storage can be untrusted. And it actually allows you to do a per column encryption key, manage encryption keys per column and even per footer in each file. And with that, you can now actually do access control too, because you can use key management services and access control on the keys stored in key management services in order to grant access on the data itself in those files. So this is something that you can do now with Spark since 3.2. It basically has adopted this Parquet encryption here. The best practice, as I said, is really to use it with a key management service. But Parquet encryption comes with a simple built-in in-memory key management store, but it's just for development. You shouldn't use it for production. And the best practice is then you don't pass around keys, right, by value. You just pass around references to the keys stored in the key protect service. Like for instance, here in this example, we are doing this with Spark. And that's basically the best practice to do that. Also here, I want to call out what's left, what's next to do. Obviously, again, integration with the table formats is outstanding. And also standardization of these key mappings in a metadata store, right? So this allows you to do the access control via metadata, but if you manage the key mappings, which key for which column, actually through Hive Metastore, for instance. And finally, I want to call out the integration with confidential compute so that you can really ensure and enforce that decryption is only possible of this column in a certain CPU enclave. There are projects also that are interesting here that you should follow, like Opaque, which does that exactly for Spark and Spark SQL. Okay, finally in this list today, I want to look at the automation aspects, pipeline automation in the data lakehouse. And for that, first remember the picture we started with, right? So it's this whole life cycle of data. Data comes from somewhere and needs to travel through multiple stages and evolutions until it's really ready for analytics, and then the analytics is actually conducted. Also, even that needs to be automated. How do you do that? Now, here are different aspects that we need to unpeel here. One is the real-time aspect of it. So you can have real-time pipelines of data that really is existing in motion. If you have that data and how to tackle that in a pipeline fashion, you can work actually with Spark and Flink as two good engines that can work on this data, because they can both work on topic data out of the box. And then you can build Spark applications, Flink applications that are basically representing pipelines, real-time pipelines. You should, however, consider maybe to pack that into an orchestration framework on top, like for instance Apache Beam. Apache Beam supports both Flink and Spark as so-called Beam runners, actually runtime environments that it can drive. And the good thing is that it prepares you also for new fancy new frameworks that are coming up right now for computing. For instance, Ray is here to mention that there's an Apache Beam project going on by the Anyscale guys that are behind Ray with the Amazon retail guys to adopt that for real-time pipelines with Apache Beam on Ray. Now, a real-time pipeline can be something very simple. For instance, it can just be a stream data landing. You take data that comes from a real-time topic, and you just take it continuously and write it into your lakehouse persistently, for instance, into Iceberg, leveraging all of these nice benefits of consistency that we saw beforehand. But it also can mean really transformations on the wire, so a topic-to-topic transformation. And then, of course, you can imagine that you may want to basically stage or put it in sequence multiple of these transformations, and that's actually a real-time pipelining combination. A special thing that's said about if your data actually is not existing in real time yet, but in systems of record. Here, actually, I want to point out a replication mechanism from Debezium, actually open source change data capture mechanism that can read change logs from any kind of source systems, relational databases, SAP systems, and so on, and write it into some target system. And this now includes Iceberg. So it has so-called Iceberg consumer, it can write it to Iceberg. And with that, you can go from there in your lakehouse and consume it with the lakehouse query engines. But finally, ETL as more the classic way to do pipelines, and where you have basically batch type of ETL steps. Also Spark here, this is the hour of Spark. This is really where Spark's sweet spot is. And there are many open workflow frameworks available that can be used to drive Spark applications and Spark jobs, like for instance Airflow, but also Kubeflow if you're in a containerized environment. What we at IBM are using as a pattern very successfully many times is actually to use this in the context of serverless functions. Function as a service, in Amazon we would call it Lambda, because they support event triggers on data, like you can have a new object that is written to object storage that triggers a function. That function triggers a Spark job, right? So you can entirely automate it that way. And then you can also combine multiple functions into a sequence and run whole sequence whenever such an event happens. Okay, so this is basically the overview of how basically various forms of open source projects enable data lakehouse concept, the rise of data lakehouse. And you can judge for yourself whether this is enough or will be enough to really achieve the goal really to unify and take on all of the data warehouse workload. I think this is not decided yet, but it definitely will eat into that domain a lot. I'm sure of that. And I'm also not guaranteeing this is exhaustive, right? This is what I'm exposed to, and I want to share with you in the following a little bit the environment that I'm working on, where we are actually adopting a lot of that, or actually all of that as we go down the road with my own environment where I'm coming from at IBM. So what we have actually is, or we call it the serverless data lake platform today in IBM Cloud, because these services here are available really entirely pay as you go. The center of that is a service called SQL Query, IBM SQL Query in IBM Cloud, which does through SQL interfaces actually a broad set of features. It can do serverless data ingestion, really even from streams as a serverless streaming job that you can submit. It can do serverless batch ETL, catalog operations, DDLs, and all of that is baked in. And of course, queries itself, OLAP and so on. It's entirely built on Spark. So this runs on Apache Spark. It is a built-in Hive Metastore for a table catalog and some of those other things that we mentioned earlier, like for instance, an indexing framework, like Xschema, like I showed you in the screenshot. It works on object storage, IBM Cloud Object Storage. It's fully S3 compatible on all of these open formats that we mentioned here. But at the same time, we are also at the same level connecting to real-time data with that in Kafka. So we have a service called Event Streams. It's just a managed Kafka service. And that's also where we're getting today also the metadata from. There's a metadata service baked in here, the schema registry, Kafka schema registry. On top of that, we have orchestration, like for instance, in our Watson Studio service, there's a service for pipelines. It's based on Kubeflow pipelines, and that can be used to automate batch ETL jobs, for instance, in this data lake service. And then, as I said, we are also big into these integrations with our serverless functions, using these event triggers and the sequencing here in our own cloud. So now you can connect it to this whole thing with your own application, with Python, JDBC, plain REST API if you like. But we also have some connectors released, like for instance, Dremio, right? We have a Dremio connector that can connect to the SQL query service and push down workload there. So that's more or less where we are today, but I want to share where we're going here, because that's really adopting a lot of that what I showed you before, right? So we are really taking that as a blueprint, almost, what I showed you before, to shape actually what we call the real-time data lakehouse vision that we are building up. Still the center of this is the SQL query service here, that basically serves as a central point of attack and processing entry point. But the big thing here is that we are now planning to really centralize all of the metadata. So we're expanding heavily on our existing Hive meta store, integrating it with the schema registry so that we have one unified metadata store for data at rest and data in motion. We're using it today already to manage our index information, which indexes exist on which table, where are they located, and so on. The key mappings, as I said, is also our vision here, that this is driven by metadata, so that you can basically eventually just do a grant and a revoke statement, and that will do all of your key mappings. And obviously, we are also going to adopt the table formats here that I showed you. So finally, I want to call out that, as I said, the Kafka thing plays for us an important role. That's why we call it a real-time data lakehouse vision, because it becomes a first-class citizen, peer to object storage, which means everything you can do in object storage with query that basically a batch query that is on data at rest or a data transformation job, you can imagine you can do the same in real time. So you can do stream transformation, stream to stream, by just submitting such a SQL job, or a real-time query that just continuously reads from a topic, and just the results will be populated into a real-time dashboard. But finally, the metadata story is also something that's why we are really very, very committed to this openness that I showed you before. We really decided that this metadata, we are not doing any proprietary thing here, right? We're taking whatever is happening in the open community, so that other engines, not just our own service, but other engines, and not just Spark, also PrestoDB, Trino, Dremio, can actually directly be deployed here and used with this data lakehouse. In addition, basically, to our own serverless option to work with this data lakehouse. So that's what I've prepared for you today. Thank you very much. Thank you for your interest. This is all close to my heart, so I really would be excited if there's any question, comments, criticism, or follow-up activity. I'm really eager, if anyone is interested here, to reach out to me. This is actually my bread and butter everyday business here, so I hope you could hear that. So I think we can close the session today. Thank you very much for your attention, and talk to you at another opportunity. Thank you. Goodbye.